load the glove box, like there's not enough time for that in the practical, but you should know conceptually how to load a glove box, right? So like if you're pulling vacuum, how long do you evacuate for, refilling, etc. Knowing how to use a Schlenk line and Schlenk filtration, just Schlenk manipulations, UV vis and emission spectroscopy. We only did emission spectroscopy in DOT, but UV vis is an important one, knowing like the knowing what patterns to expect, depending on like the d orbital splitting which we talked about in CCM, and like UV vis patterns, especially like in DOT. So just knowing the trends that we talked about in the lab reports. IR. So I would say there are some, like, you don't have to know every single stretch, but there are some stretches you would be expected to know, just like the range for like where a carbonyl would fall, or the range for where a nitrosyl would fall, where CH bonds would appear. So you, yeah.
So is it in the familiar region or?
No, like you wouldn't be like you need to just know like the important stretches that we typically, like the diagnostic regions.
So just the stretches, the vibrational modes.
No.
Okay.
No, you would not be expected to know the vibrational modes. Yeah. It's just like you should know a carbonyl falls around like 2,100. Like it, just like the diagnostic stretches that we've been talking about this quarter. I didn't finish this, but we'll just start with the techniques and then we'll just like go. And if you guys have any questions, you can raise your hand and just both of us. Yeah?
The glove box, so get to know how to use it.
So I said that you don't have to know how to like, you don't actually have to use it in practical. So it wouldn't be realistic for us to like, be like, when do you press the pedal and like raise the pressure, lower the pressure.
Sorry, you're
Like you should know how to load, like conceptually what goes into loading a glove box and taking things out.
okay. Well, like
I'll be going over that, so I guess that's the first thing I can go over. All right. So glove box. I guess actually first let's define an inert atmosphere. So a lot of things that we've done in this class has centered around inert atmospheres. Does someone want to define what an inert atmosphere is and what major two techniques we've done in this class to maintain an inert atmosphere? Yeah?
It's an air-free atmosphere.
Do you want to be a little more specific?
Well, in this case, it's an atmosphere that has like an inert gas that won't mess with the air-sensitive compounds that we.
Yeah, so the ones we typically try to avoid is oxygen and water. So we typically fill, yeah. Ethylene was for a different, I wouldn't consider ethylene an inert atmosphere. I would consider nitrogen or argon usually to be an inert atmosphere.
Yeah, ethylene was just so you could add that to your compound. But yeah, inert atmosphere is nitrogen or argon for our purposes.
And just because you don't want oxygen or water to react with your compound, because those will kill your complexes. So one method we used was a glove box, and one major reason you use the glove box is for dexterity, convenience, etc. So when you bring things into the glove box, your glove box is always, one of the antechambers is always under evacuation or vacuum. So bringing things into the glove box, right? So it's always under evacuation. So the first thing you need to do is to isolate the antechamber. So does anyone remember what we call it when you close the evacuation line to its closed position? Blank vacuum.
Static vacuum.
Static vacuum. So we isolate the antechamber to static vacuum.
So that's like after you pull it back, but you haven't like flushed it nitrogen. It's like you know, if you pull, you pull a vacuum at first, and then you close the
Yeah, so it's when it was previously under active nitrogen and you just closed the valve. And you didn't add nitrogen or anything, it's just,
I thought it was like under active vacuum. No.
so active vacuum is different from static vacuum.
Okay.
So you always want to close your antechamber to static vacuum first. And then you backfill with nitrogen. N2. And then you close the refill. Open the door, bring your stuff in.
So do we close the nitrogen, like we hold nitrogen?
Yeah, so you want it under static nitrogen. And then you open the door, bring in your glassware, and then you pull vacuum. And you refill for 3 cycles. 3 cycles. Does anyone remember what number we did? 15. So then you're going to evacuate and refill 3 by 15. So the main points for this, like for bringing things in, do people know what I'm saying when I'm saying bring things in? Like imagine opening the door, putting your glassware in. So you're bringing your glassware in, your antechamber is always under active vacuum, so you want to make sure it's under static vacuum because you never want the vacuum and nitrogen open at the same time. Backfill with nitrogen, you close it to static nitrogen. Why do we close it to static nitrogen?
Do you want to know pressure difference between outside world and the antechamber?
Not exactly.
So it's this vacuum you won't be able to.
We're under static nitrogen. Why not active nitrogen?
It was, I think, rented.
Close.
Is it possible that some kind of contamination or something? Is that what it is?
There's a closet full of nitrogen and it's like flow system, you just introduce more pressure and introduce pressure. Is that what it's
So, you close the refill to static nitrogen because if you keep, so let's say like, if you have an antechamber door, like this is your inner door and this is your outer door, I think it's kind of hard to visualize it without having the actual glove box. Let's say this is the antechamber glove box. If you have this, if you're opening this door, so this is the outside world, if you open the door and this is under active nitrogen rather than static nitrogen, if there's a leak in your inner door, it can push oxygen in. So there's the chance that if you keep it under active nitrogen, there's a leak. It'll bring oxygen into your glove box. I think that's the reason. Yeah.
Regardless if there's a leak in your inner door or not, you will crash the box if you have your refill valve open
Okay.
to nitrogen. Because the plumbing, it's pulling nitrogen from the glove box. If you have the door open and the valves are aligned, yeah, oxygen just gets in, no matter what.
Yeah. So I guess the biggest thing on this, like what you would be expected to like understand for bringing things into the glove box is you usually want things under static something, right? So when you backfill with nitrogen, you want it under static vacuum. When you bring things in, you want it to bring it under static nitrogen, which Jen just explained why you would bring it to static nitrogen. And then you would bring it in, close the door, pull vacuum, and refill 3 by 15. Does anyone have any questions on just that pull? That's as much as you would be expected.
I have a question. So if we, say we're doing active nitrogen, we're pushing nitrogen out, right? But how can oxygen get in from it?
Because you're taking nitrogen from the glove box itself.
Oh, I see.
So when you're pressurizing the pore, it's from the glove box. It's not from like outer source.
Yeah, but I mean, how can oxygen get in there?
Because if nitrogen is leaving the glove box, then oxygen can get in.
Yeah.
Because you always want to keep it pressurized, right? That's, yeah. So like if you don't keep the box under static nitrogen and you open the port door, there's not gonna, so if it's under static nitrogen, that means the glove box stays pressurized, which you want it to, because you always want it to prevent the chance of oxygen getting in. If you keep it under active nitrogen, when you bring something in, then the glove box has to constantly put out that pressure, and then oxygen can get in.
Okay.
Yeah,
When you say door, are you talking about the exterior or interior door?
exterior.
Real, okay. And then after the three.
By 15, it's the same process, and you just bring it in.
Oh, okay.
Where you isolate to static vacuum, backfill, static nitrogen, bring it in.
Okay. Got it, very good. Thank you.
Okay. Do people have the sound? I can also move.
Oh, can you take a picture of it?
Sure. I just,
It's okay, you're
What?
you're not in the photos.
okay, good. I could move, but I don't feel like moving. I guess I could. It's fine. I'll move.
You're not in any of the photos, don't worry. We zoomed them in, so it's okay.
I wasn't worried about that before, but thank you for the reassurance.
Okay.
Is there anything else about the glove box I didn't mention? I think that's as much as you need to know. Like, okay, so in the practical, you will be expected to know how to like look at a Schlenk line setup and be like, that's jank or that's correct. You're also expected to be able to like set up, and you're not expected to like do a reaction because that's not enough time, but you are expected to be able to set up an apparatus, assuming that you are establishing an atmosphere. So, I guess some things just to keep in mind for just setting things up.
Oh my god, I think
Hi.
Sorry.
So you always want to grease joints. One of the main reasons we grease everything is because air, like it just makes a good seal. You always want to use Keck clips. So one of the green or yellow like clips. You want to make sure you use your tubing appropriately and your septa appropriately. And always just clean up afterwards. And also a big thing that people, so I feel like the biggest mistakes people always make is to forget to grease things. And people always forget to check your stopcocks. So if we have a setup here, I'm going to attempt to draw a Schlenk line. Oh, I can't draw straight lines.
So when we're setting up an apparatus, are we also expected to clean off the grease as well? Like disassemble and clean everything as well?
Yeah, just set up disassembly. Yeah. I don't think that's how you draw a two-way stopcock, but that's fine. Let's just assume this is open. This is open. I'm drawing a 3-neck flask in this case. That's not what a condenser is. So this is an addition funnel, I'm sorry. And then this is a condenser.
A little squiggly.
Yeah.
That's what they look like.
Yeah.
It looks great, don't worry.
Thank you. I'm really trying. And then this is your 3-neck flask. And this is your stir plate. Okay. I think that's close enough. So
It looks great, so.
thank you. So this is your, God, I can't draw an N2 inlet.
Yeah. Stopcock.
And this always had an adapter.
Will we be expected to like assemble the one from MMT specifically, or?
I will, let me finish what I'm drawing and I'll like explain with further. So, do people know what I'm trying to draw? Okay, so this is a Schlenk line. So the biggest thing in like I feel like mistakes just like in labs in general and just like from just previously teaching this class is that you like always examine where the stopcocks are open and where they're closed, right? So let's say you are just doing these reactions with the 3 neck flasks. All right, let's say these are closed for the minute just because, yeah, you don't need it. So let's say like this is closed. I'm drawing it closed as in like a knob to be perpendicular to the actual line, right? And let's say one of it is open. Does anyone remember why we don't keep valves open if they're not attached to anything?
Doesn't oppression decrease the flow from the one that you're intended to use? No?
Yeah, does anyone else have, let's say it's under vacuum, like let's say you point everything under,
You can pull up things into the tubing.
close. What is like, so okay, and then let's add one more. Why did we not use liquid nitrogen traps in the class? What can liquid nitrogen condense?
Liquid oxygen.
Oxygen. So one of the main reasons, like the biggest lab safeties anyone will ever tell you is to never leave a stopcock open to like an open environment. Like if you're not using it, if it's not connected to a setup, it cannot be open because it can pull oxygen in to the system, and if you have a trap up, condense liquid nitrogen, oxygen.
So that is open to vacuum, or?
Let's say it's open to vacuum.
Okay,
If it's open to nitrogen, you're just wasting nitrogen.
okay.
Yeah, so for our case, like we never used the liquid nitrogen trap this quarter, but if we did, then that would be a major concern, is if you left a stopcock open, you're sucking up air, and if enough of it condenses, then yeah, that's explosive.
So you typically want to keep everything closed unless you're actively using it. Another major thing that I think was kind of like glanced over in this class, but is pretty important is an MMT Nicolasine. I don't remember if we did it for Dot, and I don't remember if we did it, I think we did it for Paul. So when you set it up, let's say you're setting up this 3 neck flask for the sake of running a reflux reaction, right? Let's say you're preparing a reflux. All right, so you have 2 lines. We always had one of the lines connected to the condenser, and we always had something connected to a nitrogen inlet. The reason we had something this is a really bad nitrogen inlet, I'm sorry guys. A reason we always had a nitrogen inlet, right, is if we needed to, well, in some instances, so, I'm not explaining this very well. We had a nitrogen inlet in some cases because we were adding substrates through other, like, openings, and then we also had a condenser because if you're running a reflux reaction, you want a condenser to be there to catch the vapors and help your vapors condense back in. So anytime that your reaction is open to reflux, right? So let's say like your nitrogen inlet was open, right? And let's say this is closed. So this is closed, and this is open. It's not bad to have it open through the condenser like at all times, it's just a waste of nitrogen. So we have this open, we have this closed, we have this closed. As soon as you turn it to reflux, one of the most important things is to close the inlet is to close the nitrogen inlet and to open the nitrogen to the condenser. The reason for this, and I saw this so many times, is because you want to minimize the chances of the solvent vapors getting into the line. And even if it's under reflux, under positive pressure of nitrogen, there's still a chance, and you want to minimize that chance. So one of the most important things, I guess, with closing and opening stopcocks is to kind of be intentional about the order in which you open stuff, because if you, for example, leave this open during reflux and this closed during reflux, that's just not the most proper practice. And if you, does anyone have any questions on, is there anything you want to add to that?
Yeah, I think, can one of my students answer another reason why you should not have that stopcock close to the condenser? Brandon?
Is it to do with the pressure inside of it?
Oh, it can,
That happened, yeah, we closed it and the pressure built up and it just popped the septum in the middle out.
Wait, was that urine?
Yeah, that was out.
Yeah, so you never want to heat in a closed system. Yeah, but yeah, also the first reason. Oh, if that's open, yeah, so that, yeah.
Was the left side nitrogen go in or is that vacuum?
This is nitrogen inlet. So let's just assume that there's only nitrogen right now. So a lot of people I would see forgot to close the nitrogen inlet when you start reflux. The nitrogen inlet is there because, like, in some cases this was just a septa and then you swapped it out for a condenser, or in some cases like it was just there. But the nitrogen inlet is essentially like a Schlenk tube, so it's useful to have to put nitrogen into your system, but it needs to be closed under reflux just because of the proximity to like a boiling solution.
Oh, is it because the solution can get into the
Yeah.
tube?
So you want to minimize. You want it to be. You want it to be open to the condenser, closed to nitrogen inlet, because you want the condenser to be able to catch the vapors. Yeah.
So the condensers should be open to the vacuum?
Nitrogen. Look, we're all assuming this is all under nitrogen right now. I should have clarified. There's no vacuum in this. This is assuming that everything's inert right now, and we're setting up a reflux reaction
So left side is closed, right side should be open.
during reflux. Yeah, all under nitrogen. There's no vacuum here. Did I miss anything about stopcocks? What do you think?
One thing like that I noticed a lot, particularly in my section, just to make sure when you're assembling something on the Schlenk line, you always want to open the stopcocks on the Schlenk line first, and then your reaction flask, and then you work backwards. If you're taking something off, you isolate your flask first, and then you close the stopcocks to the Schlenk line.
You won't have to take off the little pin on the stop.
You mean the clip?
Like the metal part? Was
The
that-
clip or the wire?
Is it wire? It was like a little metal tab that we have to take off.
So yeah, the
I
clip.
think very similar, very stuff. Same.
I don't know.
What about it?
So I remember people were taking them off to make sure it's oiled or something.
Oh.
I'm not sure.
I don't know.
We did know everyone was having trouble with robots when they took apart the stop call.
Oh, it came without the metal thingy attached. So we had to grease the stop cock. Wait, this is sling line? No, sling flask with the inlet attached on the flask, right? And then but the stop cock is out. It's not attached, so we have to grease it and then put it in and then clip with the metal.
Yeah, the clip. I don't know if you have to know how to if you have to exactly clip it, but you should know that you should clip your stopcocks to
We're
stop.
not doing it, right?
I don't know.
Oh, okay.
I think you might be referring to so there's a clip and then there's the springs.
Yeah.
With the I think you're talking about the spring that you'll have to try to assemble that in the glove box.
Oh, that was
We
hell.
had the metal clip. not
Okay,
the
well,
sling.
just know, you should clip your stopcocks.
Okay.
Yeah.
Just okay. So I guess I kind of went over a lot in the setup, but I guess I should go backwards and kind of explain when you're setting up the apparatus, what you should generally remember to do. So let's say you're just attaching something to these lines. Let's say we'll just ignore these lines. So let's just put a new piece of glassware on here, right? Before, let's say you've added your chemicals. Let's say you've added your solution, right? So one of the ways we did it, right? One of the ways we got rid of air in this class was through degassing, right? So we just put a lot of positive pressure in with an outlet needle. And we use an outlet needle when degassing so that the pressure wouldn't build up. Another way of establishing an inert atmosphere before we proceed with the reaction was by evacuating and backfilling 3 times. Same thing as the glove box, right? Same idea as the glove box where you want to remove the air, pressurize with nitrogen, and do that 3 times. So in the case of MMT, I believe you degas a bunch of different solutions, and then you put them together and then evacuated and backfilled the nitrogen and then did the Schlenk filtration. So when you set up something on the Schlenk line, right, be intentional about, has this been exposed to air yet? What parts will I need to evacuate and which parts will I need to refill with nitrogen, right? So as Jennifer was talking about, right, before you ever open something to like an air sensitive thing, you wanna make sure to evacuate and refill just the line itself. And then you want to pressurize the flask, and then you wanna open the flask, and then you work backwards going the other direction, right? Because you always wanna make sure that your reaction vessel is always like protected. So, she already mentioned it, but that's just something important to keep in mind. Yeah.
Is there any difference between degassing and backfilling and evacuating? Or is it like the same?
The gas is for details.
Yeah.
Yeah, I mean like,
So, to answer your question, degassing is sticking a needle into a solution and sticking an outlet needle so that you remove any air trapped in the solution. Evacuating and backfilling can do the same thing, but it's not necessarily limited to just the solution. Do you have anything to add to that?
No, not really.
Okay.
So when you're degassing, do you put the enter needle into the headspace first, then add the outlet needle, then put that enter needle into the solution? Like is there a specific order for that, right?
I always put it into the solution and then the outlet needle. What do you do?
Yeah, pretty much. Yeah, just I think I was telling my students it's just good practice to put your inlet needle into the headspace first before just straight up putting it into the solution right away. But as far like the order of operations, I mean, as long as you have a positive flow the whole time. Yeah.
Yeah. No.
That's just with like the tubing and stuff. So like, for example, in pull, I think you set up something in the glove box and then you took it out to introduce ethylene. Well, before you can introduce your ethylene, you have a flask that the adapter part is exposed to air, so, and your tubing is exposed to air. So before you introduce your ethylene, you wanna make sure the tubing is free of air. And then you can open up your reaction flask to the ethylene.
I remember that.
Yeah.
Just to be sure, degassing is for solutions and then evacuating backfilling if there's a box or an apparatus that we
You can do both. Like, yeah, they effectively both do similar things. Like they effectively both it's the same. They both effectively remove air and pressurize with nitrogen. And then my main thing is, I guess, with the Schlenk line, understand the more. So I think the hardest lab we did this quarter was probably, like technically speaking, was MMT, because you had to use a Schlenk filter, and then once you assemble the filter, I close the stopcock, pull vacuum to filter it, etc. So I would just make sure to be familiar with the MMT Schlenk filtration, just keeping in mind the order of the steps and keeping in mind, right? The biggest thing in MMT, like I feel like usually my biggest rule of thumb is anytime you open anything, always increase the positive pressure, right? You always want to keep things under strong positive nitrogen flow. And when you want to filter, right? When you don't need nitrogen, you can keep it under static nitrogen. To filter, does anyone remember, did we put it on, what did we put it on when we filtered? Like we inverted that, perhaps. What did we put on the bottom? Like was it nitrogen or vacuum? Vacuum to pull it through. So just kind of understanding why we do those different parts.
And for the upper one, it was nitrogen.
It was static nitrogen,
okay.
because I don't think it would be as efficient if you had active nitrogen, active vacuum. Yeah.
We're not going to like redo a filtration, MMT filtration with the practical, right? Like, we don't have to shape it.
I cannot tell exactly what's on the practical. You just will not be setting up any actual reactions. Like, there will be no chemical, like, there will be, like, no chemicals is the bad choice. No reactions, just glassware.
Do we need to bring her like lab coat?
Yeah.
Makes sense, actually.
Did I miss anything? Just getting really, like, just know your steps and why you do each step. What time is it? 3:30. Okay, we're good. We're good on.
Oh, it's Angel. Is it Angel? No, it's
So, I'm just gonna say this verbally because I don't really think this needs a section to be written, but just safety, just of each lab, go through the safety section, know what hazards we're dealing with in each lab, what pyrophorics we dealt with, what in which lab, right, like you produced certain byproducts, right, there was like toxic HCl gas, there was an inhalant, there was, just know your safety hazards and just know them. Pyrophorics. Everyone know what a pyrophoric is?
Fire.
I don't think it technically has to be fire. I think it just as long as it's
flammable.
It combusts on
flammable. Yeah. So it combusts upon contact with air or water.
And you only have one instance of cryogenics, the liquid nitrogen.
Yes.
Oh, crap.
I mean, I guess the technical biggest hazard in this lab, if we put up the liquid nitrogen traps, would be liquid oxygen condensing into the trap. But we didn't do that. So, but they mentioned it in a lot of lab reports. No, lab guides.
Needle safety?
Okay.
Damn.
So I'm just gonna write spectroscopy on here. So there were some labs we did UV vis in. We did CCM. There was DOT. MMT. DOT.
We didn't do MMT.
No, I'm just thinking if there's any other ones. I think these are the two.
MMT, we have like HMR and IR.
Yeah, that's not UV vis.
Oh.
And then IR we did it for a lot of labs, right? But I'm just gonna write it out what you should CH, right? Just doesn't matter, like alkanes. So CH alkanes. What else did we cover? We did CO, NO. Those are I feel like those are the pretty big. Oh, broad OH peaks for water. So if there's water in your reaction, you'll see a broad OH peak at 3600. That's just more if you get water in your sample, but ideally there wouldn't be an OH peak. For UV vis, the biggest thing, and I feel like when I was grading a lot of these lab reports, I think the most important thing one of the most important things in this class is understanding that we're inorganic chemists, so anything that involves the UV vis probably has to do with d electrons or d to d transitions, or just not less so in the case of DOT because the molecular orbital theory is more about like valence bands and conduction bands. But in the case of like CCM, where we're looking at coordination chemistry, right? It's all about the d electrons. So, for example, if you have, let's say you have, I'll give you an example of titanium 4. So, let's say this is an octahedral complex, right? So you got your bonding, anti-bonding. So the D count of does anyone remember what the D electron count of a titanium 4 is? -4. So what's D4 minus 4? 0. So you're going to be given a periodic table, but one of the things that to familiarize yourself with is to understand d electron counts, right? D electron counts, you go to the periodic table, you count the number of valence electrons it has total, and but depending on its oxidation state, you subtract that oxidation state to give you the D count, right? So in this case, right, it has 4 D electrons, but because it's oxidized by 4 electrons, its formal D count is D0. So, low-hanging fruit. If there are 0 D electrons, will there be any D to D transitions?
No.
Will there be any colors in titanium-4? No. So you would not be expected to observe a UV-vis transition, at least for a D to D transition, assuming that all your ligands are just like inert.
What if you have those like aren't there some ligands that can like this thing that's CO or that can like result in like coloration?
You should ask Jen about that. That's her entire research. But like before you add any like fancy ligands, right? It doesn't really have color. Something like nickel, right? It has inherent like in nickelocene, I think one of the questions was why was like the solution green. Nickel, I think it was 2. Is it nickel 2? What's nickel? Oh, D8. So this is a D8, right? Because it has 10 electrons minus 2 is D8. Hold on. It's not an octahedral complex. Anyway, it's a D8 complex, meaning that there are D electrons. Just ignore my inability to, you do not have to draw molecular orbital diagrams. My point was that there's gonna be color for nickel chloride, for example. Like when you guys all saw that nickel chloride is green, and that's because it has color inherent to it because of D to D transitions. So just understanding the theory behind UV-vis, right? So if the energy gap between these two increase, right, you're gonna need a higher energy wavelength to excite an electron from one band to another band, which will result in a shift of your UV-vis spectrum, right? So go back and look at how, I guess, the changes in energy, like with your orbital splitting, and how the d electron counts influence the colors and the spectroscopy of your compounds. Yeah.
So basically, like more like higher, like D8, D9, D7 will have higher energy, so it'll shift at like a lower wavelength. That will
It doesn't have to do with the D count. It has to do with how strong the ligand is.
Okay, sorry, stronger ligand field.
Yeah, because we did it with ethylene diamine, we did it with water and
EDTA.
Oh,
EDTA.
yeah.
So we had to look at nitrogen is a stronger donor to copper, so it had a stronger ligand field which split the orbital energies more, which resulted in a blue shift if you increase the ligand fields. Does that make sense? You can just ignore, well, like the most important orbitals are the T2GEG. That's like the most basic you would have to know. Yeah.
Are you going to analyze the
You should be expected to understand like a trend.
Okay, so on my DOP, so my product, the UV-vis turns out like there's like a decrease at the beginning of it, and then a little bump. I don't know what's the reason that has the big decrease going on. Because I thought it was because I think it was like something wrong with my product, but it turns out my reference data is pretty much the same thing.
We can talk about this individually. Yeah, we'll talk. If you need help like we're just gonna move on for the sake of time. But Zaid Race, what's your question?
Should we review HNMR as well?
Should they review HNMR? Probably. Like just the basics of what you had to do. You only had to do that in one lab, so like I think that's as complex as you'd have to do.
Like splitting, shifts, integration, that kind of stuff.
So like yeah, like what you had to do. I would say the post labs are a pretty good like conceptual, like for what you're expected to be tested on conceptually. Did that answer your question?
Yeah.
Yeah, like you wouldn't have to do anything crazy with NMR. We're also like not organic chemists, so we're not gonna make you like assemble a molecule like from a proton and I know you guys did that in Orgo lab, but like, you know. Okay, so we're gonna do some conceptual questions that I think are important. So let's do Nick. About 15. Did someone say something? Okay. So
We protested.
we did a lot of metallocene. What's the and let's say we got this. Actually, let's swap this out for a cobalt. Okay, so in Nick, right, we synthesized nickelocene. I didn't put it on here, but it's a metallocene with a nickel in the middle. And one of the reasons we use it in our atmosphere is because it's air sensitive, right? So nickelocene, if we do the d electron count, it gives us 20 electrons.
Is it air sensitive because it's prone to being oxidized by? Is that why it's air sensitive? Because it has the extra 2 electrons, like the instead of S20 instead of.
Yeah. So as I was meant to draw earlier, right? So the 2 orbitals that you're always gonna have to know is T2G, EG, right? This is anti-bonding, and this is bonding. So nickel 2 is a D8 complex, right? Because in its neutral form, it's 10 electrons minus 2 D8. So if you start populating the orbitals using the D count, 2, 3, 4, 5, 6, 7, 8, it begins populating the anti-bonding orbitals, making it less stable, which also makes it air sensitive because it has more than 18 electrons. Ferrocene is kind of like the ideal system, right? It has exactly 18 electrons, which is why we're not that concerned about it oxidizing or reducing anything because it's just happy sitting there. So this is cobaltocene, and I don't really know what this is called. Manganese? I don't know. I don't know if that's a real thing, but so we're gonna take a quick moment, and I want you to calculate the electron counts of these 2 complexes. I'll just tell you that this is a cobalt. Remember, it was cobalt 9? Cobalt 2 is D9.
Yep.
So, okay. Calculate the electron count, saying that this is D9. Maybe this is 7, right? 7. D7. So, let's do a quick calculation of what the electron counts would be based on that.
Would it be 19 and 21?
Let's wait for everyone to finish.
Oh, sorry.
Are we sure maybe it's 2 D5? Shouldn't it be D5? 22? So maybe it's 2 D5 or something.
Oh, yeah, it's D5.
D5, sorry.
Oh, dude, cobalt 2 is D7. Yeah.
I always get
I got
confused.
to, yeah.
Okay, wait then.
Alright. Anyway, for the sake of time, I will just tell you what the electron counts are, but if you didn't get the number, you can figure that out. This is 19 electrons. This is 17 electrons. This is 18 and this is 20. So if this is 19 electrons, right, we can expect this to also be pretty sensitive, and we would also expect this to be sensitive, right? So I guess the biggest thing in this class with electron counting is that you want 18 electrons. Like, your complexes are happy at 18 electrons because of molecular orbital theory, right? You don't populate any antibonding orbitals. So my question is, if you have cobaltocene and it's 19 electrons, does it want to give up an electron to be happy or take an electron to be happy?
Give up.
And is that oxidizing or reducing?
It's being reduced and it's oxidized. No, sorry, it's being oxidized, it's reducing something else, yeah.
So if you're losing an electron, you
Yeah.
are being oxidized.
My bad, yeah.
So you are reducing something else.
Reducing
So this is a really good reducing agent. So what would you expect this to be?
A really good oxidizer.
Oxidizing agent, because this wants to be reduced, gaining an electron. So it's oxidizing. Okay. Does that make sense to people? 18 electrons is happy. Okay. Dot. Alright, I'm gonna draw. We got quantum dot number 1, we got quantum dot number 2, and we got quantum dot number 3. So over time, right, we witness quantum dots growing bigger with time, right? So let's say this is time. So the size is increasing over time. So let's say this is your, I don't like this pen. So let's say for particle 1, this is your starting band gap. You excite an electron, you lose some to, this is a big thing that they bring up in the lab report. So let's just say like this is your actual band gap, and then you always have this thing called the Stokes shift where you excite an electron, you lose some to heat, and then you emit that photon back. But just for simplicity's sake, this is just what our band gap structure is going to look like. So would we expect the band gaps to be smaller or bigger as the size increases?
Smaller.
Yes. Sorry, because it gets bigger, so the electron's energy is lower, so the band gap is lower. Smaller, yes. Because, yeah, hold on. You get a bigger box, you get a bigger box. So your energy of your photon decreases because you have more space in the box. So you would expect for your energies to go down. So your band gap energy would look like this for a bigger quantum dot.
It's like,
And it would look like this for
it's
number
like
3.
less quantized energy levels, right?
Yeah.
Because you feel less of that quantum
Yeah.
confinement.
Yeah. Does anyone have any questions on this?
Oh, would we be expected to like predict like what the shift in like emission color would be like?
Well, so,
based on that? Yeah.
all right, what color would we, so what would we expect for the wavelength? How would we expect it to change over time?
Oh, it would increase.
The wavelength would increase, right, and it emits
So it goes from
at a similar frequency, not the same, but at a similar frequency, so it would redshift over time. Like it would start off blue, it would emit blue, and then it would emit red eventually. Yeah.
We have to explain, what's the question again? We have to explain using the box diagram for, it was one of the postdoc questions for this, we use the box diagram. The particle and box diagram.
So, the most important thing about the particle in the box is just as it's an approximation for the radius of the quantum dot. So we treat the quantum dot like a particle in a box. So as the radius of the quantum dot increases, right, we can think of it as a box getting bigger, meaning that there's more room for an electron, meaning that it's less confined. So the energy goes down over time of the photon. So to answer your question, like you should understand like the basics of particle in the box and how that relates to quantum dot. Like you do not need to know how to derive the particle in the box. You do not need to like do any like fancy math, but you should be able to understand the concepts that were brought up to you in the lab report.
So we can just use the solution, the En equals something something over something.
You don't even have to do that.
Okay.
Like, there's no, like, don't need a calculator. So whatever you don't need a calculator for, you don't need to know. Other than, like, adding. Relatable.
The equation would form something like for the
Bigger and it's more stabilized. Does that mean that it's gonna
No hydrogen.
like this is a very big replay.
I haven't seen her in like 2 weeks.
Me too, bestie. Me too.
Visual
But like I just let it go. Like it was absorbing more and more. This is the opposite.
Yes.
If it's more red and red is always bigger than purple.
Red is bigger.
Okay. This is gonna be our last one for today, just because we're almost out of time. So MMT, everybody's favorite. So the biggest thing in MMT is to understand, so in MMT we analyze the carbonyl stretching frequencies. And the way we kind of interpreted the stretching frequency of the carbonyl is based on what ligands are being substituted. So in the first example, right, we have 3 carbonyls. Second example, we swap out one of the carbonyls for a nitrosyl. And let's assume that the nitrosyl is in its linear form. And then in the third example, you're swapping out one of the carbonyls for a triphenylphosphate. So as we look at the stretching frequencies, right, what is the thing that would cause the IR stretch to decrease? Back bonding. So if the metal center is more electron rich, right, just as an approximation, if the metal center is more electron rich, right, there's more electrons to be donated into the pi star orbital of the CO, which is what we call back bonding, lowering the frequency. I feel like I didn't say that very clearly. So a more electron rich metal center equals more back bonding. So if we look at these trends here, which one has the lowest stretching frequency?
The it does is different.
So this is the lowest. And which one's the highest?
CO2.
So the only difference, so let's just think, so I guess what you would be expected to know is to rationalize why this is the highest and why this is the lowest. Does anyone want to take a stab at it? Yeah.
Well, we know that the PPH, I forget the name.
Triphenylphosphine.
Triphenylphosphine, thank you. That one is the lowest because that has the 2 substituted relatively weaker field ligands. And because they're relatively weaker field compared to the tricarbonyl, that induces more back bonding because there's more electron density on the metal center. And as a result, the wavelength of the frequency is lower.
Yeah. So that was a good explanation. Just to put it into the way I kind of have been explaining it to people is that you have 3 different ligands here. Carbonyl, in terms of like how pi accepting something is or how pi acidic something is, your nitrosyl is going to be your most like electronegative, as you may, and then CO would be your second most electronegative because it can do back bonding, and your triphenylphosphine would actually be the least electronegative, so it would probably be the most electron donating ligand. So the way I like to think about it is nitrosyl is really, really like electronegative, especially because of the positive formal charge. So between all of these 3, these 2 are already higher. Sorry, This one is already higher than this one because this has the nitrous seal. So when we did our MMT lab, the one with the nitrous seal compound, with just the nitrous seal, had the highest IR stretching frequency. And then when we look at triphenylphosphine is the most electron donating between the three of these, which means that it's donating metal electrons into the metal center, which can back bond into CO. So I don't like this question because you're changing more than one variable at a time. But the biggest gist of it is that you would be expected to be able to look at, I don't think you'd have to exactly predict anything crazier than this, but you'd be expected to look at a series of IR stretching frequencies and explain it using back bonding and how donating or withdrawing something is. Yes.
Can you say again the order of the electronegativity for those?
So this is the most electronegative. This is medium, and this is, I actually wouldn't consider this a pi acceptor. I would consider this like a weak pi acceptor, mostly sigma donor, meaning that it just donates electrons in. So a triphenylphosphine rarely is a pi acceptor. It's more of a sigma donor, meaning that it just gives electrons. Yeah.
Could you also explain it like based on the strength, the relative like back bonding strength of each ligand? That like if you have a CO and you substitute it with a ligand that's a better pi acceptor, that'll like make less electron density go to the CO.
Yeah, so I guess another way to think about it is that the nitrous seal is a really strong pi acceptor, so there's less electron density going into the back bonding of CO because it's competing with the back bonding for the CO.
Yeah, because for us, I don't know if this is our mistake on our part or something, but our lowest was we had this.
So I think there is a little ambiguity between the second and third order, because especially in the MMT lab. But if you were given like a trend, you'd be able to, and you should be expected to interpret it and rationalize it using sigma donors, back bonding,
and so the
pi acceptors.
The triphenylphosphine is the weakest pi acceptor, and
Yeah.
also most sigma.
Do people know what I'm saying when I say pi acceptor versus sigma donor? Broadly speaking, I think of a pi acceptor, it's not the most correct way of thinking it, but I think of it as like an electron withdrawing group, and I think of a sigma donor and a pi donor as electron donating groups. That's not the exact way to think about it, but that's how I think about it in organometallic complexes. If we simplify it, carbonyl is a electron withdrawing group because it has its lowest unoccupied molecular orbital is a pi star, so it's going to take electron density away from the metal. I also think of nitrous seal as an electron withdrawing group, actually a very strong one because it has the positive formal charge. And then triphenylphosphine, I think of as an electron donating group because it doesn't have it. Essentially, phosphines, like it has, if you think about it also like in terms of the lone pair, the triphenylphosphine is at a weird angle, so it doesn't accept electrons as well.
Is the nitrogen a pi star acceptor or is it just pi acceptor?
A pi acceptor.
Pi acceptor. And
We
then-
call these all, like we call them pi acceptors, we don't call them pi star.
And it's coming from the pi star from the metal. Like the metal the electrons in the metal are coming from the pi star orbital donating to the pi of the.
No, so it's taking electrons from the pi orbital of the metal into the pi star orbital of the ligand, which is why we call it a pi acceptor, because it's taking electrons away from the pi bonding orbitals.
Could you go back to the electron rich, the like relative? So would we also expect to rank the relative electron richness of the manganese center? So it's like
Based on these trends, yeah.
Okay, so it's like whichever one has the. Is it just inversely proportional to the? Okay.
Alright, so time's out. If you guys have any questions, you guys go to, I don't know if there's TA office hours, but I don't know.
I mean, I'll hold mine.
Yeah. I'll hold mine too.
Yeah.
But hopefully this was helpful. So,
Thank you.